Hi everyone, I'm Nay, and today my colleague Martijn and I will be talking about how we can improve access to untranscribed speech, particularly in the context of language documentation projects. This is joint work with my advisor Dan Jurafsky. The map you see in the background here is from the Endangered Languages project, which shows different languages that are either endangered or vulnerable. For many of these languages, there's lots of ongoing efforts to document and revitalize them. Part of these efforts involve recording audio, but recording speech is always much easier than transcribing it. At the same time, untranscribed audio is hard to search and retrieve, so this is where we can use spoken tone detection to help a bit. And this is basically voice search. So you could take a query like hello and compare the signal against different audio files in the corpus and see where there's high levels of correlations between the signals. But because you're comparing the signals directly against each other, you can end up with varying levels of retrieval performance depending on the characteristics of the signals. So especially when the speaker of the query is different from the speakers in the search corpus, and say the corpus was recorded in a noisy field site, but the query was recorded in a quiet room. In these cases, the search performance can actually be quite poor. So one of the questions we wanted to ask was, can we improve retrieval performance in these difficult cases using these self-supervised neural representations, which we'll introduce in the following slides? But the short answer is yes. It turns out that even in the worst case scenarios, you can get improvements from being about a third of the time correct to half correct, and that's not bad. We were interested in also exploring these representations a bit more, and in our explorations what we found was that for a model trained only on English speech, what tends to happen when you search for a word like arnanpa is that you can end up with matches like ananka. You can see both these words have the same manner template more or less, vowel, nasal, vowel, and so on. But the place of articulation is under-differentiated, so the retroflex nasal has been mistaken as an alveolar nasal, for example. So in today's talk, Martijn will walk you through the baseline features, which were MFCCs and bottleneck features. He'll also introduce Wave2Vec 2.0, which is the pre-trained self-supervised model that we evaluated, and also the language documentation data we use for evaluations. After that, I'll walk you through the spoken tone detection results and some of the visualizations of the representations learned by the Wave2Vec 2.0 model.
For our baseline representations, we used MFCCs and bottleneck features. The 39-dimensional MFCCs are derived directly from the speech signal, so they do not require to be pre-trained on large amounts of data. However, the quality of MFCC feature representations are highly influenced by noise. Bottleneck features are neural features extracted from a hidden layer that has a lower dimensionality compared to the surrounding layers. This may lead to features that are more robust to noise. However, time-aligned phone labels are needed to train such models, and creating such labels is time-consuming and costly. These trained models are also hard to adapt for languages that do not have such resources available. For models that use self-supervised training, like Wave2Vec 2.0, label data is no longer necessary. So instead of having humans first label the speech signal and then have a neural network learn to predict those labels, in Wave2Vec 2.0, portions of the speech signal are randomly masked, and the model learns to derive representations that are useful for reconstructing those masked parts. In our approach, we use the Wave2Vec 2.0 large model that is trained on the unlabeled LibriSpeech dataset that contains 960 hours of clean and noisy English speech. The model consists of 3 parts: an encoder network, a quantizer network, and a 24-layer transformer network. Wave2Vec 2.0 is trained with a contrastive loss function that measures how well the model can generate a quantized vector for any masked transformer input. While these models were originally evaluated by using the learned representations for speech recognition, the hidden layers of the transformer network may also capture information that is useful for other tasks. We therefore wanted to find out whether these representations might be useful for spoken term detection. Since we are particularly interested in using spoken term detection to help with language documentation projects, we use real data from ongoing language documentation projects as our evaluation data. We also made sure that we used datasets that had different characteristics. So for some datasets, the query and test items had the same speakers, and speakers were recorded in similar conditions, where for others there were different speakers and recording conditions between the query and test items. For example, in Walpuri, we have the query and test items from different speakers and recording conditions. The task is how well we can retrieve the query, which is the word papardi, in the test item. We use the standard evaluation metric in spoken term detection, which is the maximum term weighted value. This measures the proportion of queries that could be retrieved at a fixed error rate. With the default error rate, a maximum term weighted value of 0.48 indicates a system that correctly detects 48% of all queries searched, while producing at most 10 false positives for each true positive that is correctly retrieved.
So let's now have a look at the results, starting with the MFCC baseline. What you can see here is that there's a large effect of dataset characteristics on retrieval performance. So for example, the highest performance was associated with the two datasets, where for the query and test items, both the speakers and recordings were the same. But when the queries and test items are spoken by different speakers and recorded in different conditions, the retrieval performance drops to well under 20%. Moving on to bottleneck features, we can see that the retrieval performance on the hardest datasets improve a little bit, going from about 15% to 30%, but you do lose a bit of performance in the same speakers and same recordings datasets. Next, we'll look at the performance of the representations extracted from various parts of the Wave2Vec 2.0 model. First, I'll show you all the results, then we'll focus on only the highest performing layer, which for most of the datasets was Transformer Layer 11. So just looking at Transformer Layer 11, we can see that for the most difficult datasets, there's a significant improvement, going from about 30% up to 40 to 50% of queries being retrievable at an acceptable error rate. Looking at all the datasets, we can see that the retrieval performance that we get with the Transformer Layer 11 is close to the ideal outcomes, where for the same speaker and same recordings datasets, the retrieval performance is excellent. For the datasets with overlapping speakers and recordings, the performance is still good, but most importantly, for the most difficult datasets, the performance is actually quite acceptable. Another thing we can see is that retrieval performance was relatively higher on the English and Dutch datasets than on the Australian languages with similar datasets characteristics. To have a look at what might be the causes for the performance differences, we carried out an error analysis and examined some of the queries and their top matches. We found that for quite a few of the errors, the top match was a minimal pair or a near minimal pair with the query. So for example, the top match of the query anga with a velar nasal was the word ana with an alveolar nasal. Having seen this place of articulation confusions, we took a closer look at the representations by comparing how the Transformer Layer 11 represents various nasals and plosives in English and in Kadich, which, like many Australian languages, has a large number of place contrasts. We can see from the multidimensional scaling plots here that for both Kadich and English, the nasals and plosive manners end up at two separate clusters. In terms of place of articulation, it has an easier time differentiating the English labials compared to nasals and velars. But for Kadich, all the place of articulations are basically identical within the manners. It's a bigger problem for Kadich than in English, because in Kadich there are quite a few lexical contrasts based on manner. On the other hand, Kadich has very few minimal pairs based on vowels, for example. So to wrap up, we can see that spoken term detection can be used to help improve access to untranscribed speech in language documentation projects, and that self-supervised neural representations are particularly promising ways to be able to train on untranscribed speech in these lower source languages. The pre-trained model, the pre-trained English model that we evaluated under-differentiated place of contrast, which matter a lot more in the Australian languages. So one of the things we're currently piloting is ways to address this issue. So feel free to offer suggestions about this in the question and answer time. Thanks for checking out the video.